Welcome to another episode of Science to Sleep by where the wonders of the cosmos unfold softly, guiding you into a calm night of discovery and dreams. Tonight, we turn our gaze toward a traveler from the deepest reaches of interstellar space, an object known as 3I Atlas. It has journeyed for millions of years, crossing the frozen boundaries of distant star systems, wandering through the quiet corridors between suns, and now, it's on a path that will bring it close to our own world. As you settle in, let your breath slow. Picture the vastness above a sea of dark velvet dusted with light. Somewhere out there, moving silently through the cosmic tide, a fragment of another world drifts toward us. Scientists call it 3 Atlas, the third known interstellar object to visit our solar system. Tonight, we'll trace its path, explore its secrets, and reflect on what its arrival means, not just for science, but for our sense of place in the universe. So, close your eyes, let your mind float among the stars, and join me as we explore the story of 3I Atlas, now on track to reach Earth, across the immense darkness of interstellar space. There are travelers that do not belong to any one star. They move silently through the void, unbound by the gravity of any sun, drifting from system to system like messages carried on the cosmic wind. Among these rare wanderers is one that has captured the imagination of astronomers and dreamers alike, an object now known as 3I Atlas. It is small on the cosmic scale, perhaps no larger than a mountain, yet it represents something immeasurable, the bridge between our solar system and the vast unknown beyond. Its journey tells a story not only of matter and motion, but of time, solitude, and the quiet persistence of the universe itself. When 3I Atlas was first detected, it was faint, almost invisible against the blackness of the sky. The observatories that noticed it, part of the Asteroid Terrestrial Impact Last Alert System, or ATLAS, were scanning for potential threats, near-Earth asteroids that could one day pose a risk. But what they found instead was something far more mysterious. The object's trajectory didn't match anything bound to the sun. Its orbit was hyperbolic, suggesting that it came from far outside our solar system, an interstellar visitor much like Oumuamua in 2017 and Borisov in 2019. It wasn't just another comet or asteroid, it was a messenger from another corner of the galaxy. The realization dawned slowly as astronomers studied the data pouring in. The angles, the speeds, the curvature of its path, all pointed toward one conclusion. 3I Atlas had traveled light years to reach us. It had left its home long before human beings learned to look up and name the stars. For millions, perhaps billions of years, it had wandered alone, drifting through interstellar clouds, crossing the invisible boundaries that separate one stellar neighborhood from another. Now, by a quiet miracle of motion and chance, it was entering our own. There's a kind of poetry in the thought of it, a fragment of a distant system, frozen in time, carrying within it the chemistry of its origin, crossing the gulf to meet the chemistry of ours. When we speak of the return of the wanderer, it's not that 3I Atlas has been here before, but that it feels like a returning guest, one that carries echoes of the past, of everything that has ever moved between the stars. It reminds us that our solar system, for all its beauty and familiarity, is just one island in an endless ocean. And sometimes, that ocean sends something back our way. In the stillness of a telescope's gaze, the faint smudge of light that is 3I Atlas becomes more than an observation. It becomes a connection, a thread that binds us to something vast and ancient. Its light tells us about its speed, its material, its distance. And yet, it also tells us something unquantifiable, that we are not isolated in our corner of space. There are objects, remnants, travelers, and perhaps even stories, moving endlessly between stars. For astronomers, every discovery of an interstellar object is like finding a message in a bottle, cast adrift from a shore we may never see. When 3I Atlas was identified, scientists immediately began mapping its motion. The data showed that it was on a trajectory that would bring it closer to Earth's neighborhood than many had expected. Not close enough to pose a threat. The universe seldom works with such drama, but close enough to be studied in exquisite detail. Telescopes across the world prepared to catch its passage, eager to decode what secrets it might reveal about the matter that forms beyond our sun's reach. But for those who simply listen to the story of Three-Eye Atlas, the significance is quieter, more reflective. It speaks of the timeless drift of things, of matter that refuses to remain still. The universe is full of such movement. Stars are born, live, and die. Their ashes scatter into clouds. Those clouds condense into new stars, new worlds, and new fragments like this one. Somewhere long ago, Three-Eye Atlas was part of such a cycle. Maybe it belonged to a world orbiting another sun, one that met its end in a cataclysmic explosion, or a slow unraveling. Maybe the gravity of that dying star hurled it into the cold expanse, setting it on a path that would one day bring it near our home. And now, as it glides silently through our sky, it carries that ancient history, a story written not in words but in ice, dust, and metal. The frozen molecules on its surface could contain traces of the conditions that existed when its home system was young. Its composition might hold hints of different isotopes, unfamiliar ratios of carbon and oxygen, unique fingerprints that tell us how chemistry unfolds under another sun. In that sense, Three-Eye Atlas is both a relic and a revelation, a time capsule that predates our species, now arriving where we can finally observe it. The Wanderer's return is also a reminder of how connected everything in the cosmos truly is. The atoms that form our bodies, our air, our oceans, all were once parts of stars. They drifted, collided, and reassembled until they found a home here. The same may be true for fragments like Three-Eye Atlas. It might be composed of the same elemental threads that someday seeded planets like ours. Perhaps the dust it carries has touched other worlds, other skies, before finding its way toward this one. When scientists train their instruments on Three-Eye Atlas, they are not merely looking at a comet or asteroid. They are reading a page from the cosmic archive. Every bit of light reflected off its surface is data information about temperature, structure, and composition, but it's also a whisper from deep time. For a moment, humanity's technology and curiosity meet a piece of the galaxy that has traveled farther than any probe we have ever launched. In that meeting, science becomes something more intimate, a shared silence between worlds. So, as we think of Three-Eye Atlas approaching, it helps to imagine not a collision or a spectacle, but a gentle passing, a silent crossing of paths. Earth moves through space at thousands of miles per hour, orbiting the sun like a dancer in a vast performance. Three-Eye Atlas moves along a different rhythm, a line traced by gravity and ancient chance. When those paths intersect, even distantly, something profound happens. We are reminded that space is not empty, that the stars are not alone, and that sometimes the universe itself comes a little closer to say hello through the arrival of a traveler from beyond. To understand Three-Eye Atlas, we must first imagine the vastness of the cosmic wilderness. It comes from beyond the reach of our solar system lies a region so remote that sunlight fades into a faint echo, a place where gravity loosens its grip and the familiar laws of planetary motion begin to dissolve into the quiet of the interstellar medium. It is out there, somewhere beyond the Oort cloud, a spherical halo of icy debris that marks the farthest edge of our sun's influence that the story of Three-Eye Atlas most likely began. To trace its origins is to reach back through both time and distance, into a realm where stars are born, systems collide, and matter drifts for millions of years before ever encountering another light. Astronomers believe that interstellar objects like Three-Eye Atlas are fragments of other solar systems, the cosmic leftovers of formation and destruction. When a young star forms, it is surrounded by a swirling disk of dust and gas. Within that disk, particles collide, stick, and grow, forming asteroids, comets, and eventually planets. But this process is chaotic, and gravity does not always play fair. Large worlds can fling smaller bodies outward, ejecting them entirely from their systems. Over countless millennia, these exiles drift away into the dark between stars. Three-Eye Atlas may be one such exile, a fragment of a world that was cast out before its home system even settled into balance. when scientists began studying the motion of 3I Atlas. They found clues hidden in its orbit. Its trajectory was not just slightly curved, it was hyperbolic, meaning it was traveling fast enough to escape the sun's gravity completely. This confirmed that it did not originate within our solar system. Every known planet, asteroid, and comet is bound to the sun's pull, looping around it in ellipses. But a hyperbolic path means the object came from elsewhere, flying in on one side, and destined to exit forever on the other. It is the unmistakable signature of an interstellar traveler. To calculate such an orbit is a delicate process. Astronomers use precise measurements of position and velocity, often gathered from telescopes around the world, to model the object's motion under the influence of gravity. They must account for tiny effects, such as radiation, pressure from sunlight, or the faint jets of gas that can escape from a comet's surface as it warms. The data from Atlas and other observatories allowed scientists to simulate 3I Atlas's past journey, tracing its path backward through space. The numbers pointed to a distant origin beyond the heliopause, in a direction toward the constellation Lyra, somewhere out there, perhaps near a sun-like star. This object was once part of a larger system before being cast out into the interstellar void. Each interstellar object carries a kind of cosmic fingerprint and orbital vector that, when traced backward, may intersect with the local motions of nearby stars. In the case of 3I Atlas, astronomers use stellar motion data from the Gaia mission, a European Space Agency observatory that precisely maps the positions and velocities of more than 1 billion stars. By comparing 3I Atlas's trajectory with the movement of stars over the past few million years, they searched for possible encounters, moments when the object's path might have crossed near another stellar system. These simulations suggested that 3I Atlas could have been ejected from a young, dynamic region of the galaxy, perhaps a cluster where stars form close together and gravitational interactions are intense. The ejection of such an object would have been a violent process, but one that is common in stellar nurseries. As giant planets form, they perturb the orbits of smaller bodies, slingshotting some inward toward their star and flinging others outward with enough speed to break free completely. Over time, billions of these fragments fill the galaxy, wandering indefinitely until they chance upon another system. Ours, for example. In this sense, 3I Atlas is not an isolated phenomenon, but part of a grand galactic exchange of material. The dust, rocks, and ice that make up its body are pieces of another world's history, now visiting ours. What makes tracing the origin of 3I Atlas even more fascinating is the subtle information carried in its light. As sunlight reflects off its surface, it reveals clues about composition. Early spectroscopic observations hinted at complex organic compounds, molecules of carbon and hydrogen similar to those found on comets native to our solar system. This suggests that, despite its foreign origin, the chemistry of distant systems may not be so different from our own. Perhaps the same building blocks that seeded life here are scattered everywhere, waiting to drift into new environments. In the faint glow of 3I Atlas's tail, we see the possibility of shared origins, the idea that life's ingredients are universal, carried by wanderers across the interstellar gulf. As researchers continue to monitor it, 3I Atlas becomes more than an object of curiosity. It becomes a clue to the galaxy's interconnectedness. Its icy composition might hold isotopic ratios that differ slightly from those found in local comets, a sign of the unique conditions in the nebula where it formed. Its dust particles, when analyzed through remote spectroscopy, may reveal different balances of deuterium, carbon monoxide, and cyanide. Each difference tells a story about temperature, distance from a parent star, and even the star's age and metallicity. To trace these details is to reconstruct an entire solar system that no longer exists, to map the fingerprints of creation across the vastness of space. Yet the process of discovery is slow, meticulous, and poetic in its own way. Night after night, telescopes around the world gather faint photons reflected off the surface of 3I Atlas. Each bit of light has traveled millions of miles to reach us, carrying data encrypted in its spectrum. Scientists separate those wavelengths, looking for familiar lines, the telltale marks of water, ammonia, methane, and carbon. Every reading deepens the profile of this traveler, building a story one particle at a time. It is a quiet collaboration between technology and patience, a conversation across unimaginable distances. The most compelling mystery of tracing its origins lies not just in where 3I Atlas came from, but in what that means for us. If such objects are common, and the discoveries of Oumuamua, Borisov, and now 3I Atlas suggest they are, then the space between stars is not empty at all. It is filled with the drifting remnants of creation, carrying with them the chemistry of countless worlds. Each time one passes through our solar system, we get a fleeting glimpse of what lies beyond. Each is a visitor from the galaxy's farthest corners, bringing news written in the language of atoms and light. When scientists speak of tracing the origins of 3I Atlas, they are not merely solving a puzzle of motion. They are reading a story that began long before humanity existed. A story written by gravity and time, by collisions and expulsions, by the relentless churn of stellar birth and death. The line traced backward through space is not just a path. It is a thread connecting us to the history of the galaxy itself. Every calculation, every observation, every spark of curiosity brings us closer to understanding how the cosmos recycles its own matter, how stars give birth to planets, and how even a small, icy fragment like 3I Atlas can become a messenger from another world, carrying whispers from the dawn of creation across the infinite dark. In every great scientific discovery, there is a quiet instant when observation becomes revelation, when scattered data points suddenly align into a truth so astonishing that it takes a moment for the human mind to accept it. For astronomers studying 3I Atlas, that moment came not in a dramatic flash, but in the soft hum of computation, the glow of screens, and the steady heartbeat of telescopes collecting light from millions of miles away. At first, 3I Atlas appeared as a faint speck against the blackness, one of countless moving dots catalogued nightly by the Asteroid Terrestrial Impact Last Alert System. It was just another entry in a vast sea of data until its motion began to betray something extraordinary. When the initial measurements were recorded, scientists assumed it was a typical comet within the solar system, perhaps a long period one returning from the distant Oort cloud. But as data accumulated over several nights, something was off. Its velocity, even after accounting for solar radiation and gravitational pull, was too high. It was moving faster than any comet bound to the sun could reasonably travel. Orbital solutions that should have looped back in long, slow ellipses instead extended outward, never to return. The numbers pointed to something almost unbelievable. The object wasn't orbiting the sun at all. It was passing by it. The realization spread quietly, first among the observatory teams who ran the calculations, then through the global network of astronomers who review near-Earth objects. At first, there was skepticism. The data needed to be confirmed, and such extraordinary claims require extraordinary evidence. But as independent teams verified the readings, using data from Pan-STARRS, the European Space Agency's Gaia mission, and ground-based observatories in Chile, Hawaii, and Arizona, the conclusion solidified. 3I Atlas was traveling on a hyperbolic trajectory. It had entered the solar system from interstellar space, and was on its way back out again. There's a profound stillness in moments like that, when science pierces through mystery. The people behind the screens, the observers at their instruments, feel something deeper than discovery, a shared awe that stretches beyond equations. For years, interstellar objects were the stuff of theory. Astronomers had long predicted that material ejected from other star systems must drift among the stars, but detecting one was nearly impossible. Then came Oumuamua, the first recorded interstellar visitor, and Borisov, the second, a comet with a clearly visible tail. Yet the discovery of 3I Atlas carried a unique resonance. It was not just another interstellar object passing by. It was following a path that would bring it nearer to Earth's orbital region than either of its predecessors. As astronomers refined the data, They began to model the future course of 3I Atlas. The result sparked excitement across the international scientific community. It was on track for a passage through the inner solar system, close enough to be studied by both optical and radio telescopes. Its brightness, faint now, would increase as it neared the sun. The implications were enormous. For the first time, researchers could prepare in advance for the arrival of an interstellar object to watch, measure, and analyze it with unprecedented precision. This wasn't just another random discovery. It was an opportunity, a second chance at something that had eluded humanity for most of its history. But for all the data and simulation, there was an emotional current running beneath the science. The idea that an object born around another star was now visiting ours stirred something deep and ancient. Human beings have always looked to the sky and wondered about other worlds. Now, one of those worlds, or at least a piece of it, had come to us. In that sense, the moment of realization wasn't confined to observatories and data servers. It was shared by everyone who gazed at the stars and understood what it meant. The confirmation process was meticulous. Every variable had to be checked, every anomaly accounted for. Observatories across different hemispheres coordinated their findings, triangulating the position and velocity of 3I Atlas to eliminate uncertainty. Even small effects, like the pressure of sunlight on its surface or the faint release of gas as it warmed, were modeled to ensure accuracy. When all the corrections were made, the conclusion held firm. Its eccentricity, the measure of how much an orbit deviates from a circle, was greater than 1, a mathematical signature of escape velocity. The numbers did not lie. 3I Atlas was an interstellar traveler, just the third ever observed. The announcement spread quickly through the astronomical community, carried in emails, publications, and quiet astonishment. To the public, it sounded simple, another object passing through space, but to those who understood the math, it represented something extraordinary. Every interstellar object we observe is a fragment of a different cosmic story, a messenger from a place we may never see. The moment of realization was not just about movement through space. It was about connection through time. The light reflecting from 3I Atlas had begun its journey long before humanity learned to write, before the continents took their modern shape, before our sun had even completed a single orbit of the galaxy since life first emerged on Earth. What followed was a rush of preparation. Astronomers began scheduling telescope time, coordinating with radio observatories and spectroscopy labs. NASA's Planetary Defense Coordination Office, usually focused on potential threats, took a keen interest as well, not out of alarm, but curiosity. 3I Atlas posed no danger, but its approach offered a rare scientific opportunity. Instruments that had once watched for hazardous asteroids were now aimed at a cosmic wanderer from another star. The same systems designed to protect Earth were about to help humanity learn more about the galaxy. The public imagination, too, was captured by the story. News outlets began reporting on the new interstellar visitor, and social media lit up with images of glowing comets and artistic depictions of icy travelers drifting through the stars. But what most people didn't see was the quiet diligence behind the scenes. Teams of researchers working through the night, processing streams of data, refining the object's predicted path by fractions of a degree. The sense of wonder wasn't loud or cinematic. It was measured, methodical, reverent. To those studying it, the most remarkable thing was the precision with which they could now watch an interstellar object evolve in real time. Unlike Oumuamua, which had already begun its retreat by the time it was discovered, 3I Atlas was still on approach. This meant astronomers could observe its interaction with solar radiation, its outgassing behavior, its spin, and even its color changes as it neared the inner solar system. It was as if the universe had granted humanity a slow-motion view of something ancient crossing into our domain. For scientists who devote their lives to studying celestial motion, this was the moment when theory became tangible. The equations describing interstellar exchange, gravitational ejection, and hyperbolic drift were no longer abstract. They were real, visible, and measurable in the light of a single object now heading toward us. To trace its approach was to watch the machinery of the galaxy in action. The silent choreography of gravity that binds and releases, that connects systems separated by unimaginable distances. The moment of realization was both scientific and philosophical. It reminded astronomers that the cosmos is not static. The space between stars, once thought empty, is alive with motion, with fragments like Three-Eye Atlas that travel endlessly, bearing witness to the shared material heritage of the galaxy. Each one is a link between worlds, a carrier of stories written not in words, but in ice and stone, forged in the fire of creation and carried across light years of solitude. And as the data continued to flow, as orbit projections became more certain and light curves more refined, the wonder deepened. Humanity had caught sight of a traveler that had journeyed farther than any spacecraft, older than any recorded civilization, and now, by some quiet cosmic alignment, it was coming within reach of our instruments and our imagination in the boundless theater of the cosmos. Motion is constant, yet almost imperceptible. Stars drift in stately orbits around the galactic center, planets sweep silently along their paths, and fragments like Three-Eye Atlas cut through the dark at unimaginable speeds. Yet despite the ceaseless activity, space itself remains eerily still. There is no sound, no roar of engines, no ripple of atmosphere to carry vibration. The universe moves in silence, its music written in light and gravity. And as Three-Eye Atlas races toward the inner solar system, it becomes a symbol of this paradox. Immense velocity wrapped in perfect quiet. To understand just how fast Three-Eye Atlas travels, one must first grasp the scale of space. In the vacuum beyond our world, speed takes on a new meaning. Here on Earth, the sound barrier, roughly 767 miles per hour, once seemed an impossible threshold, but in space, that is barely a whisper of motion. Earth itself hurtles around the sun at about 67,000 miles per hour, and even that enormous velocity is nothing compared to the speeds achieved by interstellar objects. When astronomers measured the motion of Three-Eye Atlas, they found it traveling at tens of kilometers per second, moving so swiftly that it could cross the distance from the moon to Earth in just a few hours. Such speed is not generated by engines or fuel, but by the ancient gravitational slingshots that set it free millions of years ago. The origin of that speed is cosmic history. Long ago, when Three-Eye Atlas was still part of its parent star system, gravitational interactions with larger bodies likely flung it outward. In young systems, giant planets can act as celestial catapults, accelerating smaller bodies to escape velocity. Once an object breaks free from its star's gravitational pull, it becomes an interstellar traveler, moving endlessly along a straight line till another gravity well bends its course. This is the story written into the motion of Three-Eye Atlas, a relic of a distant world, still carrying the kinetic energy of its ejection like an eternal echo. As it glides into our region of the galaxy, Three-Eye Atlas is influenced by the gravity of the sun, the pull of planets, and even the subtle tug of passing stars. These forces alter its trajectory slightly, curving its path just enough to bring it near Earth's orbit. But through it all, the silence persists. The frictionless vacuum offers no resistance, no sound, no heat from passing air. In the human imagination, speed is often tied to noise, the roar of engines, the rush of wind, the trembling of metal. But in space, velocity is invisible. The object streaks across the cosmic black without fanfare, its motion betrayed only by faint light reflected from the sun. For astronomers watching from Earth, this silence is both haunting and humbling. The universe, in all its activity, conducts itself in stillness. Even the most violent cosmic events, supernova, black hole mergers, and galactic collisions, emit no sound. Their energies ripple as gravitational waves or streams of radiation, yet the human ear would hear nothing. Three-Eye Atlas, by contrast, is gentle in its passage, yet it embodies that same fundamental quiet. It moves through a medium so thin that even a cubic centimeter of space contains fewer atoms than a perfect vacuum on Earth. If one could stand upon its surface, a frozen plain of rock and dust, one would see stars, motionless, and hear nothing at all. In that stillness lies a strange kind of beauty. The motion of Three-Eye Atlas is governed by pure physics, by Newton's and Einstein's laws that describe gravity and momentum. It does not need propulsion or purpose. Its speed is the memory of its past. Every kilometer per second it travels is a record of the forces that shaped it. The silence of its journey is not emptiness, but equilibrium, a perfect balance of motion and calm that defines the universe itself. The stars are not noisy because they do not collide with air. They radiate their energy through light, invisible waves that cross the cosmos quietly. When scientists observe Three-Eye Atlas, they measure its velocity by studying how its light shifts as it approaches or recedes. This is the Doppler effect, the same principle that makes a passing siren change pitch on Earth. But in space, it is silent. The wavelengths of reflected sunlight stretch or compress depending on the object's speed relative to us. In those minute changes of color, astronomers can calculate how fast it moves and in which direction. These calculations transform the invisible silence into data, turning quiet light into a story of movement. Through this process, Three-Eye Atlas becomes not just a distant traveler, but a living measurement of cosmic dynamics. For the human imagination, it is almost impossible to truly feel the scale of such velocity. The numbers are too vast, the distances too overwhelming. Yet thinking of Three-Eye Atlas hurtling through the solar system evokes a deep sense of perspective. Every second, it travels farther than any aircraft could in an hour. It passes through space untouched, bearing the frozen chemistry of another world, unaltered by the friction that slows all motion on Earth. It is a kind of eternal glide, the perfection of inertia in a universe too vast for resistance. There is also a certain meditative quality in contemplating that silence. In the great quiet of the cosmos, time feels different. There are no sounds to mark moments, no winds to erode surfaces, no echoes to return. The only rhythm is the slow procession of light and motion. Astronomers often speak of the deep silence of space, not as absence, but as presence, a vast, steady stillness that holds everything. For listeners, the thought of Three-Eye Atlas traveling in this manner can bring an almost hypnotic peace. It is motion without chaos, speed without noise, energy without disturbance. This balance between velocity and quiet is what gives Three-Eye Atlas its poetic power. It is both a force of nature and a whisper from the galaxy. Its approach toward the inner solar system is fast enough to defy imagination, yet from our perspective, it drifts slowly across the sky. This contrast reveals how scale distorts perception. What seems still to our eyes is, in reality, a rush through the infinite. The stars themselves, which appear frozen in their constellations, are moving at hundreds of kilometers per second, but distance hides their motion, just as silence conceals the energy of the cosmos. In the context of human experience, the journey of Three-Eye Atlas mirrors our own attempts to find meaning within vastness. We too move at incredible speeds, orbiting the sun, spinning with Earth, carried around the galactic center, yet we feel still. Our lives unfold in the hush of that cosmic velocity. The silence of space is the same silence that surrounds us every night when we look up and see the stars. We are already part of that motion, though our senses cannot detect it. Three-Eye Atlas, in its fleeting passage, becomes a reminder of this truth, that motion and quiet can coexist, that speed does not always mean chaos, and that even in a universe alive with energy, peace is the natural state of things. For scientists, the speed and silence of Three-Eye Atlas represent both a challenge and a revelation. Its rapid motion makes observation difficult, but that very swiftness also provides a rare window into the mechanics of interstellar drift. Its silence, meanwhile, speaks of the universe's serene order, a realm where vast energies move in harmony without sound or disturbance. It is a phenomenon that transcends measurement, something felt as much as studied, where the human sense of awe meets the quiet mathematics of the stars. Every object that travels through the cosmos carries a kind of fingerprint, a record of where it came from and what it has endured. For astronomers, deciphering the composition of 3I Atlas is like reading an ancient script written in light. Each molecule, each particle of dust, and each reflection of sunlight offers a clue about the birthplace of this interstellar visitor. To study it is to peer into a chemistry lab billions of years old, where stars forged elements and gravity sculpted matter into new worlds. 3I Atlas, though small and distant, is a sample of another solar system delivered across interstellar space, untouched by the forces that shape our own neighborhood of planets and moons. When telescopes first turned toward 3I Atlas, they detected a faint, diffuse glow sunlight reflected off icy grains surrounding a rocky nucleus. This was the first hint that the object might share characteristics with comets rather than asteroids. Comets are known as time capsules of the early solar system, preserving the original materials from which planets formed. If 3I Atlas is similar, it would mean that astronomers were witnessing, for the first time, the raw material of another star's creation. Its spectrum, the pattern of light and color emitted or absorbed, became the key to unlocking its secrets. Spectroscopy, the study of light broken into its component wavelengths, allows scientists to identify the chemical ingredients of celestial objects. When light passes through or reflects off a material, certain wavelengths are absorbed depending on the atoms and molecules present. These absorption lines form unique signatures, like barcodes, for each element. Observations of 3I Atlas from both ground-based and orbital telescopes revealed several such features, suggesting the presence of water ice, carbon compounds, and traces of metals, materials common in comets, but arranged in unfamiliar proportions. It was immediately clear that 3I Atlas was not made from the same blend of ingredients found in the early solar system. Its chemical fingerprint was alien, yet oddly familiar, hinting at universal processes that bind all stars together. One of the most fascinating findings was the possible detection of complex organic molecules, carbon-based compounds that are precursors to life. These same molecules have been found on comets like 67P Churyumov-Gerasimenko and in the interstellar dust clouds where stars are born. Their presence on 3I Atlas suggests that the chemistry of life is not unique to Earth or even to our solar system. Instead, it may be woven into the fabric of the galaxy itself, forming naturally in the cold depths between stars. Each icy fragment drifting through space could carry within it the seeds of biological potential. Scattered across billions of years and light years alike, the composition of 3I Atlas also tells a story of extremes of ice hardened by cold so deep that even nitrogen and oxygen become solid, and of dust grains compacted by cosmic rays over eons of travel. Interstellar space is not empty. It is filled with high-energy particles, radiation, and magnetic fields that gradually alter the surfaces of objects passing through it. This constant bombardment can darken ice, transform simple molecules into complex organics, and create a protective crust of carbon-rich residue. The surface of 3I Atlas likely bears this, weathering a dark, matte coating that hides brighter, fresher material underneath. If a fragment of it were ever recovered, it might reveal layers that tell the story of both its origin and its long, lonely voyage. Astronomers have also examined how sunlight interacts with 3I Atlas as it nears the inner solar system. As it warms, volatile ices begin to sublimate to transform directly from solid to gas. This process releases dust and vapor, forming a faint coma, the characteristic haze that surrounds comets. By measuring the rate and composition of this outgassing, scientists can infer what lies beneath the surface. Early analyses indicated that 3I Atlas might contain a mixture of water ice, carbon dioxide, and perhaps frozen hydrocarbons, along with trace amounts of ammonia and cyanide compounds. These substances are fragile and could only have formed in the deep cold of interstellar space or in the outermost regions of a distant planetary system. Each observation deepens the sense of wonder. The spectral lines tell of temperatures colder than anything experienced on Earth, of chemistry frozen since the dawn of its home star. Some of its atoms may have originated in supernova explosions billions of years ago, recycled through generations of stars before coalescing into this one small body. Within its icy grains, the history of stellar evolution is recorded in atomic detail. Iron from dying stars, oxygen from giant nebulae, carbon forged in the hearts of red giants, all combine to form the dust and ice that make up 3I Atlas. It is, in a very real sense, a piece of the galaxy's memory, holding within it the record of creation. What makes this interstellar signature so remarkable is not just what it reveals, but how it compares to what we already know. Comets native to our solar system contain similar elements, but often in different proportions. The ratio of hydrogen to deuterium, for instance, a key indicator of an object's formation temperature, can vary dramatically depending on where in a system a comet originated. Measuring that ratio in 3I Atlas offers clues to the conditions of its birth. If its hydrogen to deuterium ratio differs significantly from comets here, it suggests it formed around a cooler or hotter star, or perhaps in a region with a different chemical balance. This kind of data helps astronomers understand how diverse planetary systems can be, how each star builds its world from slightly different raw materials. The analysis of dust released by 3I Atlas also contributes to the broader picture of galactic chemistry. As the sun's radiation pushes tiny grains away from the nucleus, instruments can study how they scatter light. Some particles may contain silicates, metallic oxides, or complex organics, each revealing a layer of the object's internal composition. These findings help scientists refine models of interstellar dust, the material from which all stars and planets eventually form. In this way, 3I Atlas serves not only as an object of curiosity, but as a sample of the building blocks that shape entire worlds. To many astronomers, this interstellar composition offers a poetic glimpse into unity within diversity. Every star, no matter how distant, draws from the same galactic reservoir of matter. Yet each system refines that matter differently, crafting unique combinations of elements and compounds. When an object like 3I Atlas travels from one system to another, it carries that uniqueness with it, allowing us to compare, to contrast, and to learn. It is as if the universe is slowly exchanging notes between its stellar civilizations, one comet, one fragment at a time. And though we cannot yet touch 3I Atlas, the light it reflects tells us enough to imagine what it would feel like: the frozen surface, brittle under cosmic cold, dust, fine as ash, the faint scent of ammonia and carbon as it warms in sunlight. It is a sensory experience only science can paint in the imagination, built from data, yet alive with texture. Each reading from a telescope becomes a brushstroke, each spectral line a whisper from another world. Through 3I Atlas, we glimpse the raw, universal artistry of the cosmos, a chemistry that repeats across light years, yet never quite the same twice, bound together by gravity, time, and the quiet persistence of interstellar creation. As 3I Atlas continues on its trajectory toward the inner solar system, a growing wave of excitement and urgency sweeps through the global scientific community. The realization that humanity has another chance to study an interstellar object up close has reignited conversations that began during the brief visits of one Oumuamua in 2017 and two Borisov in 2019. Those encounters were fleeting, too sudden and too fast for any spacecraft to intercept, but 3I Atlas is different. Its projected path and slower approach give scientists the rare opportunity to prepare, to plan, and possibly to send a probe that could meet this interstellar traveler before it slips away again into the deep. The potential for discovery is enormous. This isn't just another comet. It is a messenger from another star, a piece of another planetary system. And for astronomers, planetary scientists, and astrobiologists alike, it represents a scientific frontier unlike any other. From the moment its interstellar origin was confirmed, agencies like NASA, ESA, and JAXA began to model various mission scenarios. The first challenge was trajectory alignment. To reach 3I Atlas, a spacecraft must match its velocity and intercept it at a precise point along its solar orbit, a feat that requires careful timing and immense energy. Yet technological advances in propulsion and rapid mission design now make such a task more feasible than ever before. The growing use of solar electric propulsion, compact nuclear batteries, and lightweight composite materials gives engineers new tools to pursue a fast-tracked mission. Concepts like the Interstellar Probe Initiative and the Comet Interceptor mission, which already aim to study distant comets and possible interstellar visitors, are being re-examined and reimagined with 3i Atlas in mind. The anticipation also extends to the data-gathering potential. Ground-based and orbital observatories have already begun coordinating a global observation campaign. From infrared satellites like the James Webb Space Telescope to radio networks such as ALMA and optical observatories across both hemispheres, every available eye is being turned toward 3i Atlas. The idea is to capture every stage of its journey from its early, cold state as a dim speck in the outer solar system to its warming, active phase as sunlight begins to vaporize its icy shell. Observers hope to measure its gas emissions, rotational dynamics, dust composition, and perhaps even its magnetic properties. Each observation feeds into a growing database that will help scientists reconstruct its shape, spin, and material structure in remarkable detail, even before a potential spacecraft encounter. As data accumulates, scientists are also working on predictive models. They simulate how 3i Atlas will behave as it draws closer to the Sun, how much material it will shed, how bright its coma will grow, and whether any fragmentation might occur. These models are essential not just for safety, but for mission design. A spacecraft approaching a disintegrating body must be prepared for unpredictable particle environments and debris. The lessons learned from comet encounters like Rosetta's mission to 67P and NASA's Deep Impact experiment on Temple 1 provide valuable insight into how to navigate these dangers. But with 3i Atlas, the challenge is magnified by its alien nature. No one knows exactly how an interstellar comet will react under solar heating. Its ices may be composed of exotic compounds with boiling points unlike anything observed locally, and its dust grains could behave differently when exposed to solar wind. This uncertainty makes the planning process both thrilling and daunting. The idea of a rapid response mission has become one of the central focuses of discussion. Unlike traditional deep space missions that take a decade or more to design and launch, a response to 3i Atlas must be done in years, perhaps even months. NASA's Innovative Advanced Concepts (NIAC) program and private aerospace firms have begun drafting conceptual studies for small, high-speed interceptors equipped with lightweight scientific payloads. These craft could be launched aboard heavy lift rockets and use gravity assists from Earth or Venus to accelerate toward their target. One design under consideration involves using solar sails, thin, reflective sheets that harness sunlight for propulsion to achieve the necessary velocity. Others explore compact, I-don't engines capable of continuous acceleration, giving a spacecraft the flexibility to adjust its path dynamically as new orbital data comes in. Beyond the engineering, the mission planning also involves delicate coordination between international partners. Space exploration has long been a collaborative effort, but the pursuit of an interstellar object brings an even deeper sense of unity. Every nation with a telescope, a tracking station, or a research institute has a role to play. Scientists from across the world are sharing data in real time, refining orbital calculations, and comparing observations across different wavelengths. The European Space Agency has proposed integrating their upcoming Comet Interceptor framework to allow redirection toward 3i Atlas, while NASA explores a parallel strategy through its Planetary Defense Coordination Office to evaluate close approach dynamics. Even amateur astronomers are contributing, using backyard telescopes to provide brightness measurements that help refine models of its rotation and surface activity. At the core of this anticipation lies one fundamental question. What will 3i Atlas reveal about the chemistry and evolution of other planetary systems? If a spacecraft were to reach it, instruments could directly sample its coma or dust tail, measuring isotopic ratios and identifying molecules never before seen in the solar system. Mass spectrometers, dust analyzers, and imaging systems would return data capable of rewriting the story of how matter forms and evolves in interstellar environments. scientists hope to learn whether the basic elements of life, organic compounds, amino acid precursors, and complex hydrocarbons exist universally, forming wherever the conditions are right, or if they are unique to our corner of the galaxy. This is not just a question of astronomy, it is a question of origin and existence itself. Even without a physical mission, the scientific potential is immense. Every photon of light reflected by 3I Atlas carries information across millions of miles. By measuring the polarization and wavelength of that light, researchers can deduce the texture of its surface, the composition of its dust, and the density of its coma. Radio telescopes can probe for molecular emissions like hydroxyl or cyanide radicals, providing chemical fingerprints of its volatile materials. Meanwhile, the James Webb Space Telescope, observing in infrared, can detect subtle heat signatures and track how sunlight penetrates the dusty envelope, revealing clues about its internal structure. All of this data will help astronomers build an unprecedented three-dimensional model of an interstellar visitor, transforming theory into tangible understanding. Public anticipation mirrors the scientific excitement. Just as the world once watched the first images from the Rosetta mission or the dramatic close-up of Pluto by New Horizons, people now look to the sky with curiosity and wonder at 3I Atlas. Documentaries, digital simulations, and educational programs are already being developed to help audiences grasp the magnitude of this event. It's more than just a comet, it's a bridge between star systems, a cosmic enver crossing the void. For many, it symbolizes the unity of exploration and the boundless curiosity that defines the human spirit. Amid the excitement, scientists remain aware of the fleeting nature of such opportunities. Interstellar objects like 3I Atlas spend only a short time within the reach of our instruments. The window for observation is measured in months, not years. Once it passes the sun and slingshots back into interstellar space, it may never return. Every telescope pointed at it, every experiment planned, and every image captured represents a race against time. That awareness fuels a quiet intensity among astronomers who know that moments like this define generations of discovery. The anticipation surrounding 3I Atlas, therefore, is more than just academic. It's emotional, philosophical, and deeply human. It represents the rare intersection of preparation and chance, where the machinery of science meets the unpredictability of the cosmos. For every scientist poring over data or sketching mission trajectories, there is a sense of standing at the edge of something historic, a reminder that, in the vast expanse of space, we are not isolated observers, but participants in an unfolding cosmic dialogue carried by dust, ice, and starlight. Revelation that 3I Atlas is on a trajectory bringing it closer to Earth than any known interstellar object before has ignited a complex mixture of fascination, urgency, and reflection among scientists, policymakers, and the general public. For the scientific community, this is not a story of danger, but of opportunity, an unprecedented chance to study an alien visitor within our cosmic neighborhood. Yet, the implications of its passage are profound, extending far beyond the boundaries of astronomy. It challenges how humanity perceives its place in the universe, rekindles discussions about interstellar exploration, and opens new pathways for global scientific cooperation. The potential impact of 3I Atlas reaches across disciplines from planetary science and chemistry to philosophy and cultural understanding, marking it is one of the most significant celestial events of the century. When astronomers first calculated its trajectory, one of the earliest public concerns was whether 3I Atlas posed any physical risk to Earth. The answer, grounded firmly in observation and orbital mechanics, is no. Its path, though passing through the inner solar system, will remain at a safe distance far enough that there is no possibility of collision. But the very fact that it will come close enough to be observed in detail offers something even more valuable: a front-row seat to interstellar science in action. For months, observatories will track its brightness, shape, and composition, while instruments in orbit will collect data about the gases and particles it releases as it nears the sun. the proximity allows for a resolution never before achieved with such an object, transforming what would normally be a distant mystery into a near-field laboratory. For scientists, this represents a rare convergence of timing and technology, with telescopes like the James Webb Space Telescope operating in infrared, the Vera C. Rubin Observatory preparing to map the sky in unprecedented detail, and upcoming missions like NASA's Comet Interceptor ready to respond to transient cosmic visitors. 3I Atlas arrives at a moment when humanity is most capable of studying it. The object's visit serves as a proving ground for rapid coordination science, where data from multiple platforms, space-based, ground-based, and even airborne, can be combined in real time. This model of scientific agility is likely to shape how future astronomical phenomena are approached. Whether they be comets, asteroids, or even distant exoplanetary transits, the broader impact on planetary science is immense. Every sample of dust or spectral signature captured from 3I Atlas could reveal how other solar systems form and evolve. Understanding its isotopic ratios and molecular composition allows scientists to compare its chemistry to that of comets native to our own system. If 3I Atlas exhibits different proportions of water, carbon monoxide, or organics, it may indicate that planetary formation processes vary widely across the galaxy. This could challenge existing models of how habitable environments arise, influencing how future telescopes search for life around other stars. If the building blocks of life are found to be common across systems, it strengthens the argument that life itself may be a galactic phenomenon rather than a local anomaly. Beyond chemistry and composition, 3I Atlas's arrival also impacts the physics of how interstellar objects move. Studying its orbit and the subtle effects of solar radiation, pressure, outgassing, and gravitational perturbations will refine our understanding of interstellar dynamics. The more precisely scientists can measure its motion, the better they can predict how such objects are ejected from their home systems and how often they pass through ours. This has direct implications for the detection of future interstellar bodies. Astronomers estimate that thousands of such objects may be drifting invisibly through our solar system at any given time. The insights gained from tracking 3I Atlas could help refine search algorithms and sensor designs, ensuring that the next interstellar visitor does not go unnoticed until it is long gone. The potential for public engagement is equally significant. Few astronomical events capture global attention like a celestial visitor visible to the naked eye. As 3I Atlas brightens, it may become a spectacle in the night sky, a glowing thread among the stars that invites wonder and curiosity. For educators, it presents a perfect moment to connect the public to science, to explain not just what this object is, but why it matters. Museums, observatories, and science communicators across the world are already preparing exhibits and broadcasts to help audiences experience the event. It's an opportunity to remind people that the universe is not distant or static. It is alive, dynamic, and filled with travelers from other suns. Within the scientific community, the collaborative nature of 3I Atlas's study represents a milestone in how knowledge is shared. Data collected by one observatory is being distributed globally within hours, enabling real-time analysis and interpretation. Artificial intelligence systems are assisting astronomers by processing terabytes of imagery, identifying patterns that human eyes might miss. This level of integration across nations, institutions, and even machine-human partnerships marks a turning point in scientific methodology. The study of 3I Atlas may well become a model for future research on transient astronomical phenomena, demonstrating how agility, openness, and collaboration can lead to deeper insights. Philosophically, the arrival of an interstellar object so close to Earth invites reflection on humanity's connection to the greater cosmos. For centuries, humans have looked to the stars and wondered whether other worlds exist, whether life elsewhere shares our chemistry, and whether the universe itself follows universal patterns of creation. 3I Atlas provides a tangible reminder that the boundaries between star systems are not impassable. Matter travels between them, carrying with it the history of alien suns, and the dust of long-lost planets. In that sense, our solar system is not isolated, but part of a grand, interconnected galactic ecosystem. The particles that make up 3I Atlas may one day become part of another world, just as some of our own cometary material may already be drifting among distant stars. For researchers in astrobiology, this event carries a deep scientific resonance. Interstellar objects like 3I Atlas might act as natural couriers, spreading organic compounds and prebiotic molecules across the galaxy. This idea, known as panspermia, has long been debated, but each new interstellar visitor brings fresh data to test it. If 3I Atlas contains amino acid precursors or complex organics similar to those found in our own comets, it could strengthen the hypothesis that the ingredients for life are transported freely through space, seeding young planetary systems. Such findings would not only reshape scientific theories, but would also profoundly influence humanity's understanding of life's universality and resilience. Economically and politically, the interest in 3I Atlas has triggered discussions about rapid response space missions and the funding structures that make them possible. Governments and private organizations alike recognize the value of being able to launch a probe quickly when unique cosmic opportunities arise. A successful mission to 3I Atlas could demonstrate the effectiveness of public-private partnerships in space science, paving the way for future ventures that combine governmental expertise with commercial innovation. Companies specializing in miniature spacecraft, autonomous navigation, and advanced propulsion are watching closely, seeing in this moment both a challenge and a chance to contribute to humanity's next great scientific leap. Even within the arts and humanities, the story of 3I Atlas is stirring inspiration. Writers, filmmakers, and musicians are finding in it a metaphor for discovery and connection, a symbol of how small fragments from distant worlds can bridge unimaginable distances. In classrooms, students are sketching what they imagine this interstellar object might look like, learning how scientific imagination and artistic creativity often feed one another. For the scientific community, the potential impact of 3I Atlas cannot be measured only in data collected or papers published. It lies in the unifying sense of curiosity. It rekindles the collective realization that the universe is both reachable and mysterious, familiar and alien. Each observation, each discovery, adds a new piece to the mosaic of our cosmic understanding. Whether it brings new knowledge about planetary formation, the chemistry of life, or the mechanics of interstellar travel, 3I Atlas is already fulfilling its most profound role, drawing humanity's attention back to the stars and reminding us that the universe is still speaking, still sending its stories across the endless dark. Waiting for us to list. The future of interstellar research will depend on what is learned now. In this moment, when an alien fragment graces our solar system with its silent presence, each observation adds to a growing archive of interstellar knowledge, a blueprint for missions that will follow. And though 3I Atlas will eventually fade into the distance, vanishing once more into the dark between the stars, its influence will remain a guiding light for scientists, dreamers, and explorers who will carry the pursuit forward, turning curiosity into discovery and discovery into understanding. As 3I Atlas continues its silent passage through the solar system, it leaves behind more than a trail of dust and vapor. It leaves behind a legacy of awe, unity, and discovery. Its journey from another star system to ours is a reminder that the universe is not made of isolated worlds, but of connections woven across unimaginable distances. Every photon of light reflected from its surface carries the story of creation, the chemistry of distant suns, and the echo of cosmic beginnings older than Earth itself. For scientists, 3I Atlas is a once-in-a-lifetime opportunity to look beyond the boundaries of the familiar, to hold in data and theory a fragment of another world. For engineers, it is a challenge to build faster, smarter, and more responsive missions that can meet the next interstellar traveler head-on. And for all of humanity, it is a moment to pause, to look up, and to realize that we are part of something vast and living, an unfolding universe that still has stories to tell, The voyage of Three-Eye Atlas brings a quiet reassurance that discovery is endless. Even in the cold and emptiness of interstellar space, wonders move unseen, waiting for the right moment to be found. Each observation, each calculation, each question answered becomes a step forward on a journey that began long before humankind and will continue long after. It reminds us that curiosity is our greatest form of gravity, an invisible force pulling us toward the stars. As it drifts onward, Three-Eye Atlas carries with it a message written in starlight that the universe is open, infinite, and still calling to those who dare to listen. Good night, everyone.